So what are the ways to replicate the data? So there are three ways. First is the single leader approach, second is the multiple leader approach, and third is the leaderless approach. Let's discuss first the single leader approach. So in the single leader, we are having two actors. One is the leader, second is the follower. So leader can accept both read and write request, and follower can accept only the read request. So this is how the sync is happening between leader and follower. So follower can also ask data from the leader, and leader can also send the updated data to the follower. So as we discussed in the single leader, leader can only write and follower we are using only for the read only. Follower can sync the data from the leader. And here are few examples: MySQL, PostgreSQL, MongoDB, Kafka, RabbitMQ, all are supporting the single leader approach. Now this is the full diagram of single leader. Here one is the leader and two are the followers, follower 1 and follower 2. These three clients are making the request to leader. Two requests are write request, one is the read request, and these followers are only accepting the read request. This is how the sync is happening. So leader is sending the updated data to the follower, follower 1 and follower 2. Now what kind of failure we can expect from the single leader approach or architecture? So first is the follower failure, second is the leader failure. Now what is a follower failure? So let's suppose there is one leader and two are the follower, follower 1 and follower 2, and these are the data tables. So there is one client 123 that is making a write request to this leader and wanted to set the value of x equal to 1 at t0, and this leader successfully stored the value of x is equal to 1 at t0. Now at t1 the follower started the sync with the leader and sync happened successfully at t1. Same thing started by the follower 2 and the sync successfully happened at t2 for the follower 2. Now there is one user is equal to 456 making a read request to this follower 1 and wanted to get the value of x at t3 time. This follower already having the updated value of x responding back same to this client. And same thing, there is one other user that is connected to this follower 2 and trying to fetch the value of x and successfully get the value of x from the follower 2. Now what happened? Let's suppose at t5 this follower 1 is down. Follower failure is simpler as compared to the leader failure, because in the follower failure all the connected client that is connecting to that follower failed follower can connect to any other available leader or follower. In this case this user 456 can connect to any leader and this leader and this follower too. So at t6 this user 456 successfully connected with this follower too. Now what happened if the leader is failed? We will use same example. So let's suppose that t5 this leader is failed now. The problem with leader failure is leader is the only one that is accepting the write. Now after leader failure we don't have anything that can accept the write request. For that, for accepting the write request we need one leader. So for that we need to do a leader election. So after leader failure, so all the available follower will basically participate into leader election, and then after that one of them will be the new leader. So let's suppose in this case this follower one is the new leader. Now this new leader can accept read and write both. So in the same example, now this user 123 can connect to this leader and can make a write request to this leader. So let's suppose at T6 this user making a write request wanted to set the value of x equal to 2 and making a write request to this leader. So this leader successfully stored the value of x at T6 in their local storage. Once we have a new leader, then all the available followers need to reconnect with the new leader. So in this case, follower 2 is connecting to the new leader for the syncing. So at T7, this follower 2 started syncing with this leader, and at T7, that follower 2 successfully synced with the leader. Now, what are the wrong things can happen in the single leader architecture? So first is the lost data in case of asynchronous data replication. Second is the split brain problem. Third is the right time for the leader failure detection. Let's discuss first the lost data. So let's suppose there is one leader and two are the followers, follower 1 and follower 2. This leader is already having this data at t0 x equal to 1. At t1 both follower trying to sync with this leader and successfully synced and successfully store the data in their local storage. Now at t2 one new request come to this leader and that successfully persisted in their local storage t2 at t2 time y is equal to 1. Now let's suppose this leader is down now. Now these both followers are now disconnected and these both followers don't have this entry that happened at t2 time where y is equal to 1. Now after that what will happen, this follower will elect a new leader and that leader will not have that data. So that is a data loss. Now second is the split brain. So let's suppose we have a one leader and there are three followers in the system. All are connecting to this leader. So these are the data tables. At T0, one write request comes to this leader and successfully write in their local storage, that is x equal to 1. And T1 sync is successfully happened between followers and the leaders. Now after some time, let's suppose some network issue happened between follower 2, 3 and the leader 1. So now this follower 2 and follower 3 is disconnected from this leader. So but follower 1 is still connected with the leader. So from the follower 2 and follower 3 point of view, currently there is no leader in the system. So what will happen, these follower will start the leader election and then one of them will be the new leader. So let's suppose follower 2 will be the new leader now. So after that this follower 3 started syncing to the leader 2. Now from the high level point of view, currently in this system there are two leader, so that is a split brain. So both leader can accept the write here. So let's suppose at t10 two client connecting to leader 1 and leader 2. So client 1 connected to leader 1 and client connected, second client connected to leader 2. So first client making the write request at t10 z is equal to 1 and second client making the write request to leader 2 at t10 time z is equal to 10. Both leader accepted the write and both leader successfully acknowledged to the client. Now at t11 both the followers synced with the leader. So follower 3 synced with the leader 2 and successfully write the data in their local storage. Same for the follower 1. Follower 1 also successfully write the value of leader 1. After some time, let's suppose the network issue is resolved. Now what will happen, now this leader 2 and leader 1 will connect to each other and then we found conflict in the system because in the single leader architecture only there is one leader. So in this problem we are getting conflict here, and so solution of this problem is the one leader need to stop. So mostly whatever the older leader need to stop and then the folder leader converted into the follower 4. So now follower 4 started syncing with the leader 2 and rejecting the previous value of z and accepting the new value of z whatever currently in the leader 2 database. So current value of z is equal to 10. So follower 4 remove the value of z, previous value is equal to 1 and accept the z new value of z that is equal to 10. So now leader 1 converted into the follower 4. Same thing for this follower 1. So as we discussed, once the new leader is elected, so all the followers need to connect with the new leader. So in this case, follower 1 again, follower 1 connected to the leader 2 and same thing happened here. Follower 1 also remove the older value of z and accept the newer value of z here. So in this case we can see we have also a problem of data loss here because we successfully acknowledge the value of z is equal to 1 by this leader and successfully acknowledge to the that client, but due to split brain problem we have to remove the previous value of z and accept the only one value of z. So the third is the time for the leader election. So let's suppose we have a one leader and these two are follower and these two follower are syncing with this leader. Let's suppose after some time there is some network issue happened and these two followers are disconnected with the leader. Now these two followers are waiting for the leader to come up again and start the syncing process. Otherwise they need to start the leader election and then one of them will be the new leader. So once we elect the new leader, then we might lose some data because old leader might have some data that is not synced with these two follower. So for that point of view, we need to configure the leader timeout. So let's suppose the leader timeout is the 5 second. So after 5 second, these follower will start the leader election. Once we start the leader election, as we discussed, we might lose some data due to older leader might have some unsynced data. Now let's suppose what happened if we configure the timer is equal to 10 second, and let's suppose this leader network issue resolved at 6 second. Now if this network issue resolved at 6 second, we might avoid the leader election. Then we also avoid the data loss problem also here. So the problem here is with the more leader timeout or longer leader timeout is the followers are waiting more to come up or to declare the leader down or leader failure. So more leader timeout means more time to decide leader is fail or leader is working. So as we discuss small timeout and the longer timeout, leader timeout. In the small timeout, frequent leader election will happen if we configure small timeout, and if there are some temporary spike can also make database unavailable, and that could be a reason for the leader election. So longer timeout means less leader election, and smaller timeout, in the smaller timeout we can quickly identify the leader failure as compared to the longer timeout. Now we will discuss replication problems and the solutions. First is the reading on writes, second is the monotonic reads, third is the consistent prefix reads. Let's discuss first reading on writes. Let's suppose we have a one leader and we have a follower, and these are the two data tables. Now this client 123 making a write request to setting the value of x equal to 1 at t0 time, and this leader successfully saved the value of the x at time t0 and responded back to the client successfully. Now same client after writing the value again making a read request, and that read request routed to the follower at t1 time. This follower don't have the value of x, returning x equal to 0. Now client is getting the inconsistent value. Just before that client written the value on the leader, and because follower is not synced with the leader and the syncing happened at the t2 time, but at t1 request this follower returning the value of x equal to 0. How to resolve, how can we make more consistent for this user? So in this case where read is happening just after the write, for that kind of request we can routed the read request to the leader only. So let's suppose in this case the user 123 request routed to the leader, then this user will get the updated value. Second is the monotonic read. So let's suppose we have a three followers, follower 1, follower 2, follower 3, and follower 1 is having up to date data till t3 where x equal to 3. Follower 2 is one level or one step behind from the follower 1, and follower 2 is having data till t2 and where x equal to 2. Follower 3 is two step behind from the follower 1 and having data till t1 and where x equal to 1. So the user 123 making a read request to the system, and that system routed to the follower 1, and at t4 this user is getting the value of x equal to 3. Same user again making a read request, and that request routed to the follower 2, and then user is getting the value of x equal to 2 this time at t5. Previously that user got 3, now this time 2. Same user again making a read request, and that read request routed to the follower 3. Now user is getting the value of x equal to 1 and t6. So now from user point of view we are going into some past direction or some in a previous direction. Now how to resolve this problem? So to resolve this problem, always serve from one follower or one initial nodes. So let's suppose this user 123 initially connected with follower 1. So now every read request should routed to the follower 1 only. So let's suppose at t4 user is making the read request and to getting the value of x, and we are returning x equal to 3, and after t5 Now at T5 user again making a request to get the value of x. Again we are returning x equal to 3. Now at T6 again user making a read request, and that also again will go to the follower 1. Now all three requests is going to follower 1. So for this user we will always routed the request to the follower 1 only. In that way this user will get only one value. That value might be outdated, that value might be updated. Third is the consistent prefix reads. So let's suppose we have a one leader and there are two followers, and these are the three data tables, and there is one client 123 making a write request to this leader. The write request is the setting the order status placed at T1 time, setting the order status equal to delivered at T2 time. So now according to our business rule, order first place, then we can mark deliver. So same in the same sequence we have written in our leader database, at T1 time order status equal to placed, and T2 time order status equal to delivered. So let's suppose at T4 time the sync started and follower 1 started the sync, and that follower 1 could not able to get the updated data for the order status is equal to place, but follower 2 able to get the successful response from the leader, and that successfully able to successfully save the value of order status equal to place in their local storage at T4. Now at T5 another sync started for the order status equal to delivered, and both the follower able to sync or able to store the value of order status equal to deliver in their local storage. So follower 2 also successfully save the value of order status equal to deliver, and also same for the follower 1. Now follower 1 is retrying for the order status equal to place at T6 time, and the sync successfully happened, and follower 1 able to save the value of order status equal to placed at T6 time. Now the problem here is the follower 1 written the order status in wrong sequence as compared to the leader. Leader first inserted the order status equal to placed then delivered, and follower 1 inserted first delivered then placed. If client is making a request to getting the value of order status, we will serve in the wrong sequence. So follower 2 will responded back in the right sequence. Now how to resolve this problem? To resolve this problem, if any sync request is failed, then that sync request should be retried. So here, if sync request is failed at T4 for the order status equal to place, that sync request should retry from the follower 1, and at T5 that order status equal to placed, that is sync is successfully happened, and the follower 1 able to successfully save the value in their local storage, and T6 time after that, then follower 1 is basically making a request to getting the value of order delivered, and same in the same sequence the follower 1 persisting the value of order status equal to deliver at T6 time. Now we can see the sequence of the order statuses are same, and same way as we written into the leader. So this is the consistent prefix read. So sometime or most of the time we need like follower need to write in their databases or in their local storage a same sequence as leader written in their own local storage. Now what is the problem in the single leader approach? Single leader problem is the first is the single point of failure for the write. So because we are using one leader to writing the value, so then if leader is down we cannot write or we cannot serve the write request. Second is the we cannot expand geographically because there is one machine that is or one leader that is serving the write request, and that leader can be in any region. So because then the request is coming from the other region, that will be served on a very high latency. Because of that this single leader approach is not expand we cannot expand single leader approach in geo as a geographically.